What's up, everyone? This is LeetCode 235, lowest common ancestor of a binary search tree. As always, I've done this problem in Python. This is the C++ implementation. This problem is actually an easy problem, I would say. I don't know why they classified it as a medium. I think it was easy in the past, but they reclassified it for some reason. But anyways, we're given a binary search tree. Find the lowest common ancestor node of two given nodes in the binary search tree. And the lowest common ancestor is defined as it's basically between two nodes P and Q as the lowest node in T that has both P and Q as descendants, or we allowed a node to be a descendant of itself. Honestly, that explanation is kind of confusing. I think paying attention to the illustration is way easier to understand what's going on. But basically, we're given the root node, and we're given two nodes P and Q, and we need to check, is this node that we're currently on the lowest common ancestor between P and Q? If it is, return that node. If it's not, then keep going down the tree in whatever direction you need to find the lowest common ancestor. So you see how this node 2 here goes to the left, and to the right is 8, right? So this is the lowest common ancestor between 2 and 8 is actually 6. Now let's look at example 2. We're given a root node of 6, and P is 2 and Q is 4. So P and Q are both less than the current node, right? So this is not the lowest common ancestor, so we actually go left. Okay. And remember, a node can be a descendant of itself. So is 2 less than or greater than, itself, which would be, because we're on node 2, right? Is P less than or greater than 2? No, because it's equal to itself, right? And 4 is greater than, but we wouldn't want to go to the right here, because at that point 2 is not less than or greater than the current node 4, right? So this 2 is actually the lowest common ancestor of itself and 4, so we return 2. Okay, so that's what we're doing, is we're given P and Q, right? And we need to find what node is the lowest common ancestor between these two. And you can have a case like this where the actual node that you're on is equal to P or Q, and that usually in that case it's just that's the lowest common ancestor, right? So the way we do this is we're just going to call this function recursively, right? So first of all, we're going to say if root is null, right, we're just going to return 0. And this right here is just the base case. Okay. So now this is the part where we check. So let's say the p.val is greater than the root.val, and q.val is also greater than root.val. Right? So if we're on a specific node and P and Q are both greater than this current node that we're on, then we need to go to the right, right? So we're going to say return lowest common ancestor, and we're going to pass it root, and we're going to go to the right, because, right, if P and Q are greater than this current node we're on, we need to go to the right on the tree. So we're going to say root.right, and of course we need to pass it P, we need to pass it Q. Now likewise, let's say P and Q are actually less than the current root that we're on, right? Would be this, and we'd say Q.val is less than root.val, right? So if we're on a given node, like this example 2 is perfect, right? P is 2 and Q is 4. Although if we're at the root node 6, they're both less than 6. 2 and 4 are less than 6, so we actually go to the left in the tree, right? So that would be a case where we go left, so we'd say lowest common ancestor, we say root left, PQ. PQ. Right. And basically if P and Q are not greater than the current node that we're on, and it's not less than the current node that we're on, and it's not equal to null, that means that we're currently at the lowest common ancestor. So that's why we just return root if we don't actually hit any of these, right? So yeah, and these are the constraints. Like you can see, you'll always have at least 2 nodes. The number of nodes in the tree is in the range 2 to 10 to the power of 5. So you'll always have 2 nodes. But you still need the base case. Actually, no, you don't. Yeah, my bad. You technically don't need this because you'll always have 2 nodes, right? So you actually can't really have a case where you have a null node, but I think, like, personally, like, in an interview, you should still do this because it shows that you're, like, thinking about a specific base case. Or rather, a specific edge case. Because if you're like in an interview, right? You're given like these weird edge cases where you can get a null node and you don't check for that. I think you might get yourself in trouble in that interview. So you technically don't need this if statement, but it's still good practice to think about your edge cases. So just be careful of that. Right? Think through your edge cases, but technically for this problem, you don't need this if statement, but I'm still going to include it just because I think it's important to include your edge cases. This really isn't a base case either. It's just an edge case, because you could have your root node could technically be null if not in this problem, but if they made these constraints a little bit different, your root node technically could be null. So or maybe they could only give you 1 node, but they'll give you a P and Q that's both less than or both greater than the current node. I don't know. Just they could give you these weird edge cases if they wanted in an interview. So just make sure you cover your bases. But yeah. Anyways, I hope this helped, and I'll see you in the next one.